Hello, I'm Biril Chinkaya. As a first-year PhD candidate from UTAD on electrical and computer engineering, today I will present the work plan of my thesis project, which is named as A Cognitive Architecture for Human-Robot Collaboration in Field Robotics, and is being developed at Engineers R&D company in Porto. This PhD thesis falls under the area of field robotics. Field robots are adaptable and sensitive to dynamic, unstructured, and therefore challenging environments such as agriculture, forestry, constructions, and others. The question is, if they are this much suitable for these tasks, why do we still need human supervisors, and can't we just use simply fully autonomous robotic solutions as in some examples that we see in industrial applications? The reason falls under the lifelong autonomy maintenance of these systems under these challenging scenarios. Still, it is possible to combine the advantage of these robotic systems with humans' critical thinking, strategy, empathy, and physical skills, fostering a symbiotic relationship between humans and robots, enhancing efficiency and ergonomy. Therefore, there is a great potential to present scientific contributions, as this is our main motivation. Having this motivation, our main objective is designing a time-sensitive multi-agent decision-making system for a symbiotic HRC that has the capability of tackling the uncertainty of human agents' behaviors. While having the multi-robot system that runs in outdoor environments is already a challenge, having a human in the loop makes it even more difficult due to the following challenges, such as what is the intention of the other agent, when and how to perform the joint action, where to perform the joint action, how to handle the requirement of high computation power and storage capacity. To tackle these challenges, we propose three complementary objectives, which are human-like decision-making modeling with enhanced physifinite state machines, spatio-temporal decision-making with multi-agent deep reinforcement learning, and knowledge transfer and distributed processing with fog-enabled federated learning. Three tasks are identified to accomplish these objectives. Task 1 is human-like decision-making. Identifying the current human behavior and responding to it by providing adaptive control is essential in any proactive HRC architecture. However, taking human behavior into account is a challenge due to their inherent level of uncertainty. Therefore, Task 1 aims to propose an architecture that combines physiologic, deep learning, and finite state machines, which are great to model time-variant events, and enhancing it by physiologic to handle the uncertainty in human behavior data. Besides, differently than other probabilistic methods, this method can output in multiple states. Currently, a simulator that involves multi-robot systems and humans, which are controlled by users as avatars, in a dynamic forestry scenario is being developed to evaluate the approach, which might be a contribution for the community. Besides overcoming uncertainty problems, a reliable multi-agent decision-making is demanded by any safe and effective HRC architecture. Nevertheless, in interactive scenarios without representation of symbiotic relations between the agents, these methods generate low cooperative behaviors. Therefore, this task proposes to design a multi-agent spatio-temporal decision-making system to make decisions ahead of time by combining graph neural network with deep reinforcement learning. The HRC simulator will be used once again in this task to train and test GNN with DQN within a forest scenario including robots and movable playable characters triggering actions such as cutting a tree. Besides, real-world experiments will be tackled using ingenious human-related technology hardware and robots. All the previously addressed topics fall on the use of computationally demanding approaches, such as deep learning methods, which can make it unfeasible to completely execute the proposed architecture locally. Therefore, the aim of this task is to study and develop fog-enabled federated learning. This task allows for any relevant training to take place in each decentralized fog server locally, which can be then combined in the cloud and can be fetched whenever needed from any robot. Then the training models are used in runtime execution in each agent's processors, which allows each agent is able to make their own decision and communicate their decision. During accomplishing the addressed tasks, I will follow the curricular plan, includes external curricular unit, seminar, thesis planning and scheduling, thesis development. I have also selected 4 modules which are advanced topics of digital signal processing, which is already evaluated, microsensors and microactuators, biological and natural inspired algorithms and systems, and optimization and classification methods. Each methodology and evaluation results of each task will be presented in several conferences and journals that planned as ICRA workshop, which is already presented, and the paper has been titled as Empowering Field Workers, a Cognitive Architecture for Human-Robot Collaboration, IROS, the International Conference on Intelligent Robot and Systems, IEEE Roman, International Conference on Robot and Human Interactive Communication, ICRA in the main conference, the Journal of Field Robotics, and IEEE Transaction on Systems, Man and Cybernetic Systems. I would like to show my timeline, which includes the tasks, modules, and planned publications. Noting that this timeline may differ in the end according to the result of the FCT grants. And finally, I would like to demonstrate the current state of the graphical abstract of the proposed architecture. My presentation ends here. I appreciate your attention. Thank you for listening.